Hello, everybody. My name is Jayse Petersen, and my project this summer was calculating the gas fraction of galaxy mergers at the cosmic noon. And my advisor is Dr. Jehan Kartaltepe. So before we get into the nitty-gritty of this project, let's start with some basics. So first of all, what are galaxies? Galaxies are gravitationally bound systems that are made up of stars, gas, dust, dark matter, planets, and in the case of one galaxy in the middle of the cosmos, has us in it too. But as we can see, there are many different types of galaxies. I wish I could go over all of them. However, in the case of merging galaxies, typically we see mergers occur between these groups here and create galaxies in this group here. So what are galaxy mergers? Galaxy mergers are interactions and in some cases, combinations of two or more galaxies that form to create one galaxy with different properties than its constituents. And there are multiple stages of galaxy mergers. I can't go over all of them. However, broad strokes, we see gravitational disturbances as the galaxies get closer and closer and closer together, and eventually they coalesce to form one. And I'd also like to note that these pictures are not the same two galaxies. Merger timescales happen over millions to billions of years. So these are all different mergers throughout space. So the big question, right? Why is studying mergers important? So mergers have been hypothesized to play an important role in shaping the universe as we see it today. Some pretty interesting examples are starburst galaxies, elliptical galaxies, and pertaining to this project, the cosmic noon, which among other things, saw galaxies undergo a drastic physical change from kind of puffy, disky structures to more bulge-dominated structures that we see in our cosmic neighborhood today. Of course, science cannot be science without data. So this project acquired its data from ALMA, which is the Atacama Large Millimeter or Submillimeter Array. It uses 66 dishes to gain a light collecting area of over 71,000 feet. And ALMA was used because it can see the universe in very long wavelengths. And that makes gas measurements of distant galaxy mergers possible. This project used the Cosmos survey from ALMA as well. And the Cosmic Evolution Survey is a swath in the sky that encompasses a tiny region that contains millions and millions of galaxies all throughout the universe's history. And we can see some, 2.6 billion years ago, even all the way out to 10.2. The ALMA data was obtained at submillimeter wavelengths, specifically for the purpose of gas measurements. And these submillimeter wavelengths are called ALMA band 6 and band 7, which occupy 0.8 millimeters to 1.4 millimeters. And again, this was specifically for the purpose of measuring gas content in these galaxy mergers. So I made a quick flowchart of the merger detection process. Of course, it removes a lot of the head bashing that I experienced in the process. But essentially, we start out with a catalog of band 6 and 7 galaxies, which contained around 57,000 sources, and then matched it to a catalog of 1,006 confirmed mergers from Shaw et al. 2020. And around 300 mergers were returned. This 300 would have been great. However, I had to employ a signal to noise ratio cut to confirm which detections were real and which ones weren't. And I can describe what that is right now. So a signal to noise ratio is essentially a question, right? How much signal are we getting compared to the background, right? And in the case of a signal to noise ratio below 1, we can clearly see we cannot distinguish the signal from the background. If we go to around 1, it's kind of easier, right? We can see there's something happening here, but still, right? We can't really say this is a real detection. In the case of 2 and above, right, there is very clearly a signal in this pixel value graph. And we can see over here, right, it's pretty clear. Anything above 3 is perfect, right? That is almost certainly a real detection. So now, after this signal to noise ratio cut was employed, around 48 or so galaxy mergers were returned to perform gas measurements on. Come on, there we go. So I've been mentioning gas measurements, right? Gas this, gas that. So what gas am I actually looking at? And that would be the ISM, or the interstellar medium. And it is the matter that exists between the stars in a galaxy. And the reason why I'm looking at the ISM is because it's what interacts the most during mergers and interactions between galaxies, because um, because of the vast cosmic distances that are involved in galaxies. So what is a galaxy's ISM mass? It is essentially just the mass of the ISM, right? The mass of the galaxy's gas that excludes star mass and dark matter mass. And the method of finding the ISM mass was used from an equation from Scoville et al. 2016. And it involves the observed flux density, right, which was obtained from ALMA, the redshift that was obtained from Dr. Shaw in her study, Shaw et al. 2020, of course, the ALMA frequency, and the luminosity distance, which is dependent on the redshift. These values here, these 4 over here were calibration and correction constants that were calculated in Scoville et al. And for my purposes in this project, they're used as constants. And here is a plot of the 48 mergers ISM mass in 10 to the 10, oops, sorry about that, 10 to the 10 solar masses versus their redshift. As we can see, aside from some, super tall ones up here, super high ones up here, a lot of them hover between the 0 and, well, not 0, the 1 and 10 to the 10 solar mass range. So now that we have the ISM mass, we can actually now go to the gas fraction. And a gas fraction is a galaxy's ISM mass divided by its total baryonic mass. And its baryonic mass, total baryonic mass, is the ISM mass plus the stellar mass. So now here we go. Here's the plot for the merger's gas fraction versus their redshift. As you can see, again, a lot of them hover in the lower area across the all these redshifts. A lot of them hover between the 0.1 and the 0.4 range, which is kind of interesting. Again, aside from these ones that are really tall up here. So of course, seeing is believing. So once all of the ISS or gas fractions were made, I moved on to making cutouts of the mergers that I could. Unfortunately, I could only make cutouts of 31 of the 48 mergers because all of the image files in the database I was using were not available to the public yet. So here are the 31 cutouts that I could make. I would like to make a couple of notes on this. Of course, these are like, if we look at this guy over here, right, cosmic spaceship, if you didn't see that it was a spaceship, now you can't unsee it. The galaxies in this collage here don't actually look like this, right? If we were to aim the Hubble Space Telescope over at them, right, we wouldn't see a spaceship looking thing over here. The reason why is because these are plots of where the ALMA flux is, right, in the graphs. And I know you're technically not supposed to play favorites, but 598441 over here is my favorite. So I'd like to also direct your attention to another one of these cutouts, which I called the cosmic hair claw, because it kind of reminds me of a hair claw. This one is an artifact. This one is the result of this weird line shape is a result of an artifact in the interferometry process and data processing procedure from ALMA, and can happen at times when data is collected. So what are the next steps? Of course, I was only able to find detections of 48 of the 1006 mergers from Shaw et al. So that leaves the rest are undetected. So I can create cutouts of the undetected ones and stack them to create kind of an average image of all of them. And I can perform point spread function photometry on the stack to get an average flux, and then repeat the analyzation process that I've described with ISM mass and gas fraction on the average flux data to get an average ISM mass and gas fraction for this group. What I can also do with the cutouts that I have is I can plot the points of each galaxy in the merger on the cutout, right, which helps for visual identification. Because especially like as of this morning, right, I thought that the merger 598441 was between this guy and this guy here, but it turns out that the two galaxies are here and here. And this I actually excluded as a little piece of the background. So looks can be deceiving, which is why plotting points will help. I can also compare the distribution of ALMA flux with the Hubble images, like this guy here versus here. Personal results of this project. I learned code and code troubleshoot, which prior to this summer I had no idea how to do. I also learned how to work in a research group with people whose skills are much higher than my own. I learned time management skills. I met some really cool people. And I also figured out that synthwave and chillwave music is fantastic background music while working. So for some quick acknowledgements, I'd like to thank Dr. Kartaltepe for helping me learn the ropes and seeing me through this project. I'd also like to thank Isabella Cox for being an absolute wizard when it comes to Python, as well as the whole of the Galaxy Evolution group for being awesome people. And of course, RIT College of Science and the SURF program for giving me this opportunity in the first place. And thank you for your time. Questions are welcome.